for your patience, I must tell you that next conference I will organize only for Germans, because they like the schedule, so it is easy to organize things with people who follow the schedule without discussing. Okay? Okay, it is only a joke, but not so much. Now I want, everybody here knows G.Maugin. I want to give, explain a little bit the reason for which I wanted to dedicate this session to him. Gerard I met when I was a young ricercatore many years ago, and he came to Rome, the big professor from Paris, came to Rome and gave a talk to my students, I mean master students. Those times our students were good enough to understand a lecture by G.Maugin. He spoke in English to my students, and it was a total success. He got 10 minutes of standing ovations, and they knew that Gerard was not giving them notes. Okay? I was teaching to electronic engineers, and he gave a talk about the importance of field theories and interaction, piezoelectric effects, and things like that. Until I was weak, Gerard has been weak. As soon as I became stronger, I discovered the controversial sides of the character of Gerard, which is an opinionated man. So, of course, one has to accept. When we are serving truth, we need to be ready to accept opinions. There is a joke between Gerard and myself. He continued it last time. He said, I was professor in Paris. So, before giving the word to Samuel Forrest, who has something to say, I want to read to you, I'm sure that you know it, the name of the rose. I understood at that moment my master's method of reasoning, and it seemed to me quite alien to that of a philosopher who reasons by first principles, so that his intellect almost assumes the ways of the divine intellect. I understood that when he didn't have an answer, William proposed many to himself, very different one from another. I remained puzzled, but then I ventured to remark, you are still far from the solution. I am very close to one, William said, but I do not know which. Therefore, you don't have a single answer to your questions? So, if I did, I would teach theology in Paris. In Paris, do they always have the true answer? Never, William said. But they are very sure of their errors. And you, I said with childish impertinence, never commit errors? Often, he answered. But instead of conceiving only one, I imagine many. So I become the slave of no one. So I can tell you that G.Maugin, notwithstanding the fact that he is professor in Paris, is asking himself many questions, many answers, and if you discuss with him, you discover he can accept your point of view, if you argue. If you argue. So, some...
I need this. I simply wanted to share some souvenir with you. Not from Paris, in fact, but perhaps you will recognize the place. You see that there is a long connection between Euromake and generalized continua, because in 1998 there was a conference in Magdeburg, and we have several representatives of of Magdeburg in this symposium. And perhaps you remember it was on mechanics of materials because it was related to the Mecamat Association, the French one, which still exists. And we added the word intrinsic length scale, and it was organized at that time by Albrecht Bertram and François Sidorov, also there. And I wanted to show you some picture at that time. Yes.
This one.
Next. This one first. So you recognize here that we were lucky to have Eckehard Kröner. So we will speak today about... and behind, I think you recognize Professor Kinsler, who will deliver a talk after that. So you see we are in the same community. And if you look below, you will recognize, sitting close to Eckehard Kröner, you have G.Maugin, and I am pleased to show again this. Sorry for the quality, which is very bad. This is my scan of the book. It was a black and white book. And I think it's very nice to see that because, of course, this idea of revival of the generalized continua has a lot to do with the work of Kröner and a lot to do with the work of Girard also at many times. And many of us were inspired and to work in this field, which is a strange and theological field also, and the generalized continua has something to do with that. So that's why I think you recognize also Yuri Estrin, which is the third one here, who was also present in Magdeburg. Yeah? It was a beautiful place. So I think we have to thank Girard for inspiring us for continuing work in generalized continua, which is a crazy task, but we will... You came from Japan. Okay. It's a long way. It was a long way. The train were faster at that time, from Berlin to Magdeburg. Okay, so I don't take more time. Thank you very much.
Okay.
And I give it to Girard.
It works. Well, good morning, everyone. Francesco told me that I could say whatever I wanted. So first I changed the title. So it's not only second order gradients, but it's more general, so it has to be generalized. And I don't want to give many formulas. I will try to keep with pictures, nice pictures, and just to give examples where we have to consider a generalized continuum description for biomechanical problems, or sometimes I say mechanobiological problem. It depends where you put the emphasis, okay? So, let's see if it works. Classical theory continua, you deal with the first gradient of the motion, which is described on the first equation, and that's what you need, basically, in all of classical continua. And forget about the other equations. Now, I want to give one example, which I've been using many times, but I never solved the problem, because I never got the contract with the insurance company AXA. They gave the money to people who were studying banking operation in the medicament industry, instead of giving it to a scientific problem. So we missed the money, but still we thought about it. And this is essentially the problem I want to look at. You see, I want to look at the growth of long bones. You have many long bones. Of course, you have long bones here. You have a long bone here. Because the question of being long is how long it is compared to the cross-section. Okay? And this is a problem when mammals, like human beings, grow until they reach perhaps 20 years old. This happens during a lapse of 15 years. And the question is how the bone, which started like this, grows, of course, in this section here, but also in this dimension, with, let me go one step further, a close examination of this region, in which you can see that the lengthening in the bones happens by a transformation of some cartilage, chondros in Greek, chondros, and bones, real bones. So what happens is that this transition is moving up, and this part gets longer. Okay, that's exactly. But of course, the mechanism which takes place here is extremely complicated. And if you enlarge this region, now this region is conventionally called the growth plate, although in reality it doesn't look like a plate at all, but you know, that's a scheme. And if you look inside, you see that there are basically three regions. You start with kind of small particles. When you go down, they grow. And so you see that there is a kind of macrostructure there. Whether you consider the macrostructure or not, it depends if you want to have a simple model or a complicated one. So, continue with my picture. That's a real bone, okay? More or less real, I know. But, so the plate is not a plate. It looks like this. Okay? There's another view here, which is a bit more complicated. Here. Anyway, this is called plate. And so if you look inside the plate, you have a kind of structure, you see, in which you start with a reserve zone, and when you go down, you arrive at the bone structure. So you transit from cartilage to bone. Essentially two different materials, or maybe one material with changing properties in space. Depends how you look at this problem. And that's another view, artistic view of the same problem. That's more interesting. Some people measured the one elasticity coefficient in the plate, considering rabbits, okay? And you see when you go down with the plate here, and you take several rabbits, you see that the elasticity coefficient increases. So you could look at the problem as one in inhomogeneous elasticity, in which elasticity coefficient vary in space. That's one possibility. Okay? That's the end of the evolution of the zone. When you are about 20 years old, the zone has disappeared, and there remains a kind of trace here. This is the print left by the plate. This is kind of a dangerous region for fracture, okay? Something may happen later on there. So, that's a picture, a kind of cartoon of the transition zone. And those are the three ways with which you can consider to look at this problem. The first one, on the left-hand side, you have a brutal transition from one state or one phase to another one. So you look at the zone as if it were no thickness transition zone like you do in phase transition. Okay? And this belongs to the theory of configurational forces, as you know, because you must devise a theory by which you describe the driving, you can describe the driving zone, the driving force on the zone so that it progresses upward. And you change cartilage to bone. The second picture in the center is one where you think of the zone as having some finite thickness, but a lot of things happen there, and there is a microstructure. You may think of using some kind of power description. As you like, you are free to do whatever you want in this modeling. The final picture is the one on the right, which would be the ideal one. You have a zone of which the thickness varies in time until it closes to nothing. But this takes 15 years in human beings, okay? So it's on a time scale on which you are not interested here. So that was the example I wanted to give you. This is just the same as what I said verbally, the three possibilities. Just a question of the stability of this zone. You may think that if something unstable happens, the zone will develop in a strange way, and this may finally expand in some kind of pathology for the bone, okay? Something which happened with fortunately with some kids. So that was the problem. That was an example. So a gradient theory, that is an inhomogeneous material, or a material with a microstructure, or something even more complicated, which is hopeless for treatment now. Okay? So, I want to take another example which requires the consideration of a second gradient of strain. Okay. So, this can be discussed. If you have to consider second gradient, not only you have the motion, the first gradient, there's the referential gradient, you have to consider the second one. Just an historical.
You can answer the question mark.
No, I am not like St. Thomas. Unless I see the document, I will leave the mark. Because in this case, I have the proof, the written proof.
In French.
Well, it doesn't matter. It could be in the Cossack, I don't know what, something from Siberia, it would be just the same. Okay? And since Lagrange was a French scientist, and it's written there, it's not Lagrange, it's Lagrange, you see. You admit it finally. Okay? So, but this has discovered this document where, what happened with my thing? I lost it. Saint Renan, in fact, has written a short note in French, 3 pages long, where he questioned the validity of the usual theory. Maybe he would like to take an additional gradient. In problems where you have non-uniform strains, like in torsion. So this is the idea. Okay, motivation for that. Motivation comes from the fact that in 2000, my friend Iptad and me wrote a paper, a tentative approach to the growth, volumetric growth in tissues, soft tissues. And we found out that if you want to account for the import of material or energy from the outside, that is, if you have to modify the equation of continuity for mass with additional terms in the right-hand side, thermodynamically in the end, you will get a correct theory only if you include the second gradient of strain for the classical deformation. I will show that in one equation only. Okay? And so what we did is that, it was too complicated. We said, okay, there might be something which happened, but we slave the evolution of the second gradient to that of the first one. Okay? You can always do that, it's a model. Okay, so that was the motivation to go further, and that's what is written there. So in terms of medicine or surgery, as we call a transplant, the operation of changing the local material, we have to consider a second order transplant if we have a second gradient of strain. We have to account for thermodynamical compatibility. I lost the alloy, here it is. And of course, in the end, we have to find the motive power on the growth effect. Growth is a kind of local rearrangement. It has to be governed by a configurational force. This is extremely complicated, as you can imagine. Let me just show. The basic equation is either this one in the Polar-Kirchhoff framework or this one in the classical framework. You see the continuity equation is modified by a bulk term and maybe some input on the right-hand side. Now the fact that you put those two terms, or those in the classic description, time t, complicates everything. Okay. This is a traditional picture. You see, we have to consider deformation from a kind of material configuration, the actual one, the standard F, deformation gradient, its gradient, that's where the second gradient of the strain or displacement will come into the picture. And if we had only F, we would have a multiplicative decomposition between an elastic deformation and a growth deformation, following a model given by some people in the 1990s. Because we have the gradient of F in addition in this picture, there will be additional quantities coming here, like the gradient of this Fe with respect to this configuration and a complement here, which I call the growth Q. Okay, those are essentially, this is how the QG is built. It's built from the material gradient of the growth F. There is a QE, which is defined this way. But don't pay too much attention to this equation, because in 5 minutes you will have forgotten them anyway, or maybe 10 minutes. Okay, this is just to show what would be the standard equation of motion in the Piola-Kirchhoff format. That's the time derivative of momentum, external force. That comes from the growth, mechanistic growth. This comes from the fact that we have the first gradient that defines the first Piola-Kirchhoff stress. That's why there is an F. And the second one is, I always lost this, here. And the M comes into the picture, you see? The flux of matter from the outside. Okay. Don't pay attention to the boundary conditions, which have to be complicated anyway in a gradient theory. And if you want to have some nice mathematical justification for those additional boundary conditions, at the surface or along the edges of the surface, you have a reference to work by Francesco and Sepechea. Okay, that's just the same in the actual configuration. Don't pay attention to that. Okay, that's an interesting equation. Is the Clausius linear inequality which you obtain in this description? You see, you have something that comes from the first order Piola-Kirchhoff stress, which would be essentially the derivative energy with respect to F or Fe, something that comes from the second gradient, something that comes from the evolution of species which are evolving there, something which should describe the flux capital M, a standard conduction that goes with this, and heat. Now that's the interesting term. If we had not put the second gradient, we would still have this term. But this term is computed by taking the gradient of the energy, internal energy, when you keep the entropy fixed. So that's what it is. And it is this term which, if it is not balanced by second gradient effect, which causes a problem in thermodynamics. Because one would involve essentially the gradient of density, but for the mechanical part, this is equivalent to taking account of the second gradient of the displacement to the same order of magnitude. So that's what justifies the approach. Okay, I'm not going to go through the mathematics because time goes by, and that's what would be left if we accepted the definition of TF and TS. That's the equation of material forces, the configurational balance that you have in this problem. You see, it's complicated because not only you have a material momentum, you have an HLB stress which contains a classical term plus terms coming from T, the Piola-Kirchhoff stress. This looks a little bit like Euler-Lagrange derivative of the energy. Okay? Just for fun, I'll give you some expressions, but really they are useless. Okay. If you're interested in geometry, you have to reinterpret all these quantities in terms of connections in the manner of Kramer. And I will give you how you introduce connections. One is a standard definition. You take the material gradient of the inverse of the growth F, multiplied by F. That's classically connections, the connection based on F. It's a connection which is independent of the metric. It's something else. The space is more complicated than the usual space. The second connection is built like this, with my Q and this, okay? And those are two connections, and there is a differential theory which has been developed by De Leon at the time, about 10 years ago, for dealing with this combination of these two quantities. That is just for fun, if you like differential geometry, which is the case of some people, even in mechanics. Okay. Now, for those who are amateurs of the HLB stress and the evolution, you see you have to build an evolution for the, this is the rate, or more or less the rate of Fg, in F dot and F minus 1 dot, okay? And there is another term that comes from the Q. And this is what you will try to formulate equation for Lg and the quantity within parentheses to obtain possible forms of the drying forces. Okay, that's one possibility. Simple ones, I mean, relatively simple ones. Forget about this. This is the whole theory. If you are interested, it's given in two papers. One in the International Journal of Linear Mechanics, and the other one in the Journal of Mechanics and Physics of Solids. Okay, forget about these equations. I want to give a resume of what we have done. We have considered the equation of mass, which has a right-hand side, considering the material growth per unit volume and the mass transport due to the import of energy. Because this is living matter, it has to, you have to bring some energy. The growth is not just like this. We have defined quantities like stresses, first order hierarchy of stress, second order, and then from these you can construct the quantities which are in the configurational balance equations, and the morphogenetic processes are described by the variation of the concentration C alpha and the fluxes C alpha. Okay, that's another picture which shows how you go from deformation to material connection and remodeling, which consists in finding the evolution of Fg and Qg in terms of the HLB stresses of the first and second order. And now, as you know, many people consider second gradient theories of strengths because of the possibility of occurrence of singular lines on surfaces, or even apices. Think of the top of the Eiffel Tower. That's a singular point. And so mathematically, you have to envisage this possibility. Okay? This is done for a surface sigma inside the volume, but also when there is a singular line on the surface. That's what justifies the consideration of higher order gradients, at least the second order. Okay. Pictures. So what do we do with that? I want to give a few examples which are really done for fun. When we bought the cable TV in Paris, I became a fan of the channel called Animals. Before that, I had never been in the countryside, I had never seen a cow or whatever. And I became a specialist in elephants, crocodiles, whatever you find. They reproduce the same documentaries during the day and the long night if you don't sleep. So I became a specialist of all these animals, especially in South Africa and whatever there. So one is the rhinoceros, which is horn. That is not bone, of course, it's keratin, okay? Like the nails or the hair. And of course, this develops in a singular way. Another example is the horn of antelopes, so-called Thomson antelopes. Now, this Thomson is not Lord Kelvin, of course. Kelvin did a lot of things, but I don't think he spoke about antelopes. Maybe, you never know. And this is the examples that we've treated numerically. The growth of the rhinoceros horn, the growth of the antelope horn, and also the growth of some seashells, which are a complicated structure with singular lines. So that's what happens with the rhinoceros nasal horn. I will not give the explanation. It is the genetics that decide on the initial conditions. And then you let the program grow and you see the horn develops, although it takes some time for the true rhinoceros. But here, it's done instantaneously. Okay, you see the singularities which can appear in this problem. That's another case the seashell called Sinum shimba. I don't know how it is pronounced in Latin. He knows Latin much better than me, but this is also the growth, and you have to encounter the singular lines. But I don't want to speak about this one because it has to do with cancerous research, and I don't know, we pass it, okay? That's the antelope horn that develops also in this very nice way, starting with the seed, of course, and then it develops according to the theory with those singular points. Okay, let's go with this. That's another seashell to Rutella communis, something which is very frequent, as the name indicates, and you can produce the growth of this kind of animal because you create matter and you grow and you develop the system. Okay? And I am practically finished because I am on time, and so I don't know what is on the slides. Oh, the usual thanks. Not that, because this is essentially done for the public in the USA. And so it's like at the end of a movie, I promised that nobody suffered during this production, except Pasquale Ciarletta, who did the computation, and me, because I had to read the papers. So that was a kind of introduction to problems which are a little bit complicated, in my opinion, and to the opinion of readers, very much too complicated. But that's the way we do some progress in this field. Okay? Thank you.
You should include audience in that as well.
Well, the audience, especially American professors, are not concerned by this. Okay? They have to suffer to deserve this. Especially if they are from the Midwest.
I started with another example, which was from Czerkajew. It's a mathematician from
I know Czerkajew, yes.
Yes.
Sure. He's the fastest talking guy in the Middle West. Speaks.
So he spoke about the trees growing somewhere in the mountains which are twisted.
Yes. Yes.
So it's probably similar.
Probably it's the same kind of problem, yes. Except that he spoke about it. He didn't treat the problem. Did he treat the problem?
Yeah, he tried.
I tried. No, because he's too much of an analyst to do that, I guess.
But I want to come back to this growth. This is very interesting what you say, but I wonder how to find the relation between the theoretical approach and this what happens in the, I mean, during the prenatal growth, we have the cartilage. I suppose, I don't know, but I suppose that...
That's the stage before this evolution, of course.
Yeah. Then, after, in the later stage, I guess, I don't know, but I guess, also the loading, mechanical loading starts to play some role.
It does it is a very important role, yes.
The mechanism is this. We have the growth rate. On the top of the we have the cartilage, and below we have the bones.
Yeah.
And then in the cartilage we have the cells which do not require the oxygen.
Yeah.
Bone cells need oxygen.
Yes.
So we have the blood vessels in the bone.
Yeah.
We don't have blood vessels in the cartilage.
Yeah. We have seen that on the picture. You're not British from the picture.
Then the blood vessels grow. They get some signals from somewhere. I don't know.
Yeah.
They grow. They deliver the oxygen. So the mesenchymal cells, which appear, they turn into the bone cells instead of the cartilage. So
Yeah.
osteoblasts instead of chondroblasts. differentiation of the cells.
Yes, yes,
Mechanical condition.
yes.
The flow, the stem.
In fact, I had a slide which I didn't give here, which shows the influence of the mechanical load. Of course, if you could block the growth by, that would not be a good idea. There are also people who, it was a treatment for midgets in the past, try to elongate them, but it doesn't work so well. But it favors the speed of transformation, the advance of this front in a way.
Yeah. But then there's another question. Osteoarthritis.
But it's not a question to me because it's a comment.
Probably can be treated also.
Yeah.
Because osteoarthritis is the disease which causes the growth of the bone into the cartilage.
Yes.
So there are some specific regions when we have
the transition
of the bone and others. So I guess
maybe there is something to be done. Yes, I agree.